My name is Mateusz Pusz. I work at EPAM Systems, and I'm also an independent C++ trainer. Today I would like to share with you my findings regarding package management and build systems. Unfortunately, for this talk, I requested 90 minutes. I got only 45, so I had to remove a lot of material, but still we have quite a lot to cover. So I would like to ask you if it's possible to postpone longer discussions until the end of the talk if we have time, or otherwise just catch me on the break or something like this. Okay, so to not waste time, let's continue. When I was trying to submit this talk to ACCU, I got a feedback that maybe rather I should consider such a subject, Mercurial Mason Conan, and I said no way. We just already standardized something, let's say, in our environment. We use Git, we use CMake. Let's not try to differentiate our environment anymore. So I would stay with Git and CMake. Maybe this is not our favorite tool, but it seems to be an established standard already. By the way, can I see a show of hands who likes CMake and who uses CMake in the work? Maybe who uses CMake? All of you. And who of you likes CMake, in fact? Oh, there are quite a few people here liking CMake. Okay, so this is what we have right now, in my opinion. We have, let's say, something like quite an established standard for having Git as a version control system, CMake for building stuff, and for package management, we don't have anything right now as a standard thing that every project supports. But I would say that Conan is a really strong contender here, and I would like to introduce it to you today. I am in any way not related with Conan project. I just have some visual experience with that. I found it working for me, so that's why I selected it to show it for you today. First of all, I would like to maybe list typical ways of handling dependencies in our projects. Maybe once again, a quick show of hands if you use external or third-party subdirectories in your source tree to store external dependencies. Yes, like quarter of the room. Maybe you are using Git submodules for the same, using add subdirectory. The same quarter, exactly the same people. It seems so. Okay, external project act in CMake. Do you use it? Only a few people. Okay. Maybe you are downloading and installing each dependency by hand, and then using find package in CMake to find them. Yeah, again, quarter room. I think that this side is like more active. You can also try, guys. Okay, and maybe you tried using other languages toolsets like Maven, NuGet in other projects to handle dependencies. This also happens, yes. And this last one is, have you any experience with Conan already? I assume you have, at least a few of you. But this is a new tool on the market, and I would like to tell a bit more about this. Okay, so a few words about add subdirectory approach. Let's assume we have some liba that uses gtest for its internal unit tests and exports boost as an interface of its library. We are using boost 166 and gtest 180 for this lib, and we have two libs like this. We have another library that has another boost version in its submodules, for example, or in the source tree. It has OpenSSL and a different gtest. We may have a bunch of those, but for the sake of the slides, let's have only two, and have a project that uses them. And it, of course, also has its gtest version, but it uses the latest one from the Git repo. It uses different OpenSSL. And what's now? You have boost file system from one boost file system from another boost in the same libraries. How do you handle that? Yes? That doesn't scale at all, and if you can imagine that you have not only two, but like 20 libraries you use in many layers, it doesn't scale. And even if you have this as a one repo, you may have another repo on the other side, or three more, and you can end up with this approach having like 10 or 12 different boost compilations on your one machine, and you're probably out of disk space already. So this is one of the biggest problems I see with this approach. It doesn't scale and doesn't provide the coherency between dependencies, because you're using different OpenSSLs, different boosts, and it may be hard to make this work together. Okay, so let's talk about CMake a bit. CMake is not a build system, it's a cross-platform C++ build generator. Basically, this is how you use this tool. In GCC and Visual Studio, these are only the examples, because you can use, of course, different compilers. But basically, you can use only CMake and CTest to do everything. You don't have to use make, nmake, and other things. You can just say CMake build target to install it. The important part here is that you can see that for GCC, Clang, and other compilers, you may provide build type during the configuration stage of the CMake. But for IDEs that allow you to switch the debug release mode in some combo box, you provide this not in the configuration, but then in the build, test, and maybe install stage. This is important difference between those different targets. I would not talk much about CMake as a modern CMake. There was a great talk last year here by Daniel Pfeiffer. I will just maybe refer to some things that he already told you, but if you are looking for more hints on how to use CMake in a modern way, just go there. It's really great talk, and everyone using CMake should see it. Basically, the outcome from his talk is that build flags don't scale, that each change in public flags has to be propagated upwards. It's not possible to maintain those flags on the large scale, and that different projects may contain or require different conflicting flags. For example, we can think that that unique name like verbose as a preprocessor define can have for one project like values from 0 to 3, in another project values from 1 to 5. And when you make them global, how you want to configure those two projects in your source tree, for example, if this is made global, yes? And we use verbose or debug level or anything, or log level in many projects, the same name. Modern CMake is about targets and not properties. To create a target, you use those commands. You have add executable to create executable. You have add library with different options to create shared static object interface libraries. There is also a specific option for so-called alias. We'll talk about this a bit later. And also there is a possibility to create a few of those with as an imported target, meaning that the CMake will not try to build it. It will just reuse what's already built and make it a target in a CMake. Also, if you not provide any static on shared here for add library, it will depend on the build shared libs option of CMake, and based on this, it will either be shared or static. So if you will leave this and not provide anything, you can then, from external source, just configuring the project, you can say if you want to build it in a shared way or in a static way. So I would assume if you are linking static stuff into a large library, just mention it's a static. If something has to be shared, just make it shared, but the final result of your library probably shouldn't have anything there, just for the user to allow the user to specify which kind of library he wants to build. Okay, so modern CMake, it's like from 2013, I specified target XXX commands. For example, this target link libraries. What's new in this modern CMake is that you can provide private, public, and interface modes for dependencies. So basically how it works. If I need it and my dependers or users need it, it should be public. If it's needed only by me but the dependers doesn't use it because it's only my implementation detail, I use private. And when it's not needed by me but the dependers need it, for example, it's a header-only library, you provide it as an interface. Of course, the fourth option is trivial here. If no one's needed, you just don't care. What's important here is that interface and public dependencies are transitive, while private are not. What I mean by that is that if you will provide something here in library, and it has some library to link, and it has some flags and properties set, and they were public, this one will also have them in its interface for interface and public. Thanks to that, it makes CMake code much simpler, much easier, much shorter, because you don't have to remember about dependencies all the way. I will show you an example here on the graph. It turned out that I worked on quite a big project in my company. It had like 360 CMake files, and this is only a part of it. And it was not written in a modern way. So basically, you can see here that everyone depended on everything downwards. This is basically the linking diagram generated by CMake, graph this option. So let's assume that this thing got boost as a dependency with find package. It turned out that then every other library, and nearly every library here uses it, had to do find package again, had to define all the headers again, and had to link directly with the libs again in every CMake file here. Moreover, it turned out that because of that usage, sometimes, for example, this library could use headers from this library because someone just provided directory into the include directories phase. And the compiler didn't complain about this, and you had some problems with the architecture of your application, and you didn't know about it. Anyway, I would suggest you to play with GraphVis option of CMake if you're using CMake in modern way, because it can help you a lot, as you will see in another graph. One of important things, maybe here you can see that there's library hanging without anything. It didn't link with anything, actually, but it worked because everything was global, and linker did the magic for this. So it officially didn't have any dependencies, but it had. After my cleanup, the same graph looked like this. This is modern CMake with targets. It turned out that I have to introduce here some feedback loops, let's say, or SQL dependencies, because, as I said, this library used headers from this library. It was not visible on the previous graph. We have some cyclic loops here. This is a problem. And now it's visible on this architecture diagram generated by CMake. And it's much easier right now, because if this one uses boost, then all those others don't have to bother. They are just transitively progressed to all the users of this. And you can see that right now there is a layered hierarchy of the libraries, which was not the case here. It was a mess. Right now, CMake actually provides you the layers by itself. Yes, question, Titus?
So when you said that bit with boost, let me make sure that I'm understanding your scenario right.
Mm-hmm.
You're saying that if the lowest level dependency in your package
mm-hmm.
adds, or in your project adds a dependency on, say, boost, then nothing else that is higher level than that needs to mention boost?
Yeah, so the question is, if the lower level here uses boost, then if we have to mention about this up in the higher layers. No, we don't have. If you are using boost as a public dependency of your library, then all the other modules, let's say, of CMake obtaining it or linking with it will have the same property. Will know about all the header files, about all the libs they have to link in order to be linked with your library. So you don't have to repeat yourself all the time. It makes it much cleaner.
But doesn't that mean that that is a promise for all time now, that your lower level piece is always going to depend on boost? Like,
yeah, basically I think that lower levels probably are things like utils or tools module that basically uses boost and will use boost and forever for this. If you would, if you
like difference between what are we optimizing for? Is this optimizing for the usability for a human of, like, I don't have to type out a dependency on a package that I am using because there is a package that I'm already using that has that dependency? Or should you have to type out the dependencies at every level for the things that you actually use at that level?
Mm-hmm. Okay, so the question here is, if I'm using boost directly here, should I mention that I'm using boost, or just depend that one will import it? Yes. I think it depends. If you are using this directly and you depend on boost in this library, for example, you could depend here on file system. Here you could depend on the thread, for example. Then you can, of course, include different boost libraries here and different headers, and that's for sure useful. But if you are just using the interface of this library, with maybe file system being exported in its interface, then just use this library. You don't have to link with boost anytime anymore, yes?
Yes.
But As I asked in the very beginning, let's keep the longer discussions at the end because we have a lot of material and I really have only half of time for my presentation. And now we can see the real design problems, yes? Following John Lakos, don't do cyclic dependencies in your modules and components. Alias targets. I said we'll come back to the subject and we are back. Basically what it does, it allows you to have different name for the same library. What it helps you with is that this is the typical name you obtain from find package function of CMake. And it allows you, if you have different CMake files, just to refer to this in that way. And you don't care if it was just included from another CMake or it was obtained from find package command, it's the same. You don't have to have different if-defs or something like this to verify if I'm building it from find package, I have to use this name or this name. If I'm doing this directly with including of other CMake files, I have to just use the target name. So it's good practice to use alias that will look exactly the same as your find package export thing, and then reuse it. And another really useful option for package management are the generated expressions. They maybe not look too user-friendly, but they are really powerful. The difference between this and, let's say, this preprocessor ifs is that preprocessor ifs works in the configure phase. So this first line we shown in the user cases of CMake. And this one is being used in the build phase, where all the configuration is already done. And when you are building, you can build, as you see, for Visual Studio in release and in debug mode. And this is visible only in the build phase, for example, for Visual Studio. And this is exactly the case here. This is bad, this is wrong. You shouldn't never use CMake build type in if. Because as you've seen, it depends on the compiler you are targeting. For GCC Clang, it will work. For Visual Studio, it won't. Instead, just use those generated expressions. For debug, use this one. For release, use this one. And it will work correctly for your builds. Another use case is when you are having a library that will be installed on the file system. That during build phase you have to find include directory in your file tree that you are building the directory. But the users of the library, when they install it, would like to find those include files on the your install directory. Yes. So this is another use case for the generated expressions. You say that for build interface you use those directories, and for install interface you are using include in the install directory. And this is good to remember about this because otherwise you have problems after installation. This is typical modern library example. You have introduction saying what version you are using, naming of the version of the project, and maybe version if you want to share it with someone. You are having some dependencies with find package. You are defining your library. You may specify which version of standard you are using. You have some include directories, but per target, not globally provided. Which libraries do you link with? And then you can provide this alias, as I told you. Following Daniel's recommendations from last year, please avoid custom variables in the arguments. You can see there are no set here, and everything works fine. Set is wrong because it has many issues. For example, it's case sensitive, and if you will have some typo, it will just compile silently without expanding your things you thought you are expanding, and so on. To use this library, you can have, for example, unit tests or tests CMake module that has similar prefix, just enable testing. For ctest to work, you are doing find package for gtest. This is how you may use your library. Please note that this is specific if not target thing. I will refer to it later. And then I do using find package. And you define your tests and link privately with your library for testing. This is how I organize my file tree in the projects. Basically, I have two directories, one for sources, another one for tests. And what's important here is that this source have a standalone CMake lists file. I mean standalone that you may go to this directory and just build it from this place. And this file never changes the compiler warnings. please do not play with compiler flags in this thing, because then if I will include your library in my project and I have different compiler version maybe 2 years later that has better diagnostics and you enabled me WO, I don't care about your bugs that are only warnings in a compiler. I don't want to find in your CMake places where you enabled me the highest level warnings possible in GCC. It just has to compile for me. Yes, it's a dependency. I don't care about those problems. Do not play with warning flags in this file. There's another standalone directory here, tests, and you can also go to this directory and build the project. And there is a wrapper at the top that just includes those two. It's being used mainly for the development for IDEs like CLion or Visual Studio to enable you to open this as one big thing and don't have to install stuff in order to test. This is how this wrapper can look. So it's basically just add sub-projects here and here. And you have to enable testing again because it has to be on the highest level of CMake in order to work for C-test. OK. How are we doing on time? Following Daniel's recommendations, don't use this. And don't glob files. Avoid variables. Don't play with CXX flags directly. And a few more things I will not scope right now because we are really tight of time. OK, so we compiled stuff and we are done, yes? This is how many library authors think about their projects. If it compiles, that it's fine, I have my project running great. No, this is asocial code, as David Sankal said a few years ago here. We shouldn't think only about ourselves. We should share our project and make it easy to obtain by others. This is the file tree. I would like to have it installed in my, for example, local directory. Yes? I would like to my headers being exported and all the CMake configuration of all the targets being exported. And of course, the binaries. And this is how I do it. Basically, this is the abbreviated version of the CMake we had earlier with the most important parts here. And you have to provide install with targets my library and provide all the directories you would like to install. And you build basically this exports here. Then you can say that this exports has to be exported to the specific directory and specific file configuration for this. And the namespace, this one that we use in alias too, yes? This is a lot of boilerplate. I admit I don't like it, but it's needed for the project to work properly. I hope it will be made a bit easier for later. I did some macros for me to play with it and make it easier. You can find it on my GitHub repository, but I didn't put it here. Then you also have to copy all your public headers for project, and you also have to provide the version file and install everything with your configuration to specific location. Your config file may be really trivial, saying just you want to find dependency full for version 1.0 and just include this targets file that was created on the previous slide. OK, so what is the workflow I would like to suggest you for testing of this? Go to the source build directory and build your library and install it. Yes, so you're checking if it builds correctly. You are installing it, and then go to the test directory. That is also standalone, as I said. Build and install. Use this installed location for and test. So basically, what it does, it builds and installs stuff to your disk, and then checks if the package is correctly installed, and tests run with it. So this is another approach, rather than using this global standalone highest CMake that is being used for development on every build, yes, you use on your machine, where you are just building and using unit tests at the same moment. You rather may also test your installation stuff that way. And that's in fact, by the way, why it was so important to have this if not target in one of the CMakes, because at some point, sometimes if you're using this higher level CMake, the target is already defined because it was created by add subdirectory to source. But in this case, you will not have this target created. You will have to find it by find dependency, find package, yes, in order to make it work. So this is why this was their if in the previous slides. However, CMake is not the final solution for our package handling and dependencies. You have to build each repository in isolation, generate and install things to your disks, and then find package for all of it. There are problems if you want to recompile stuff, or you want to support different versions or different compilers, for example. You want to build it for GCC, for Visual Studio, for Clang at the same machine, for debug, for release, for, I don't know, release with dep info. Maybe you would like to use different runtime libraries in Visual Studio, or different package configurations, with exceptions, without exceptions, specific debug warning levels, or whatever you have as a preprocessor commands. All of this makes different options, and installing this on your machine and then referring to them with find package will be really, really hard if you have like 20 different configurations for each package. And I think these are the things that every one of us would like to have, talking about the package management. One builds projects and all the dependencies. Only things that are required are being rebuilt if needed. Reuse pre-built binaries wherever possible. No need to manually download stuff, build and install. It should be done by the package manager, yes? A possibility to use our own versions. So if you have some zlib or boost installed on your file system, you want to use maybe your own version that is much, much newer or older maybe for some dependency or compatibility checking than the one that is installed on the system. And with that, I think that Conan addresses all of those features. That's why I wanted to show you that tool today. Conan, first of all, is open source software, and it's for free. So you can use it anywhere you want. This is decentralized like Git. It's huge advantage here. Servers are dummy. They are just the package storage. They do nothing interesting there. They are just keeping the data. All the logic is done in the client. It's responsible for pre-building binaries, for building from sources, and so on. It's portable. It can be used wherever Python can be used. It also uses Python for its scripting language. It works with any build system. CMake is one of the possibilities here. I scope on CMake here because, as I said, it's de facto standard right now in our environment, but you can use it with PureMake or other things. And it's easy to host. This is basically how Conan servers looks. We have three possibilities here. We have either simple application Conan server that is also open sourced, or we can use a JFrog Artifactory or JFrog Beantray to store things. Those are available for open source software for free, at least Beantray. But also, as I mentioned here, a JFrog Artifactory Community Edition was released, like I think in February this year, for C++, and you can just use it in your company. This is high quality server with Conan for free. We are using this already at EPAM. And basically, to start working with Conan, you have to understand how the identifier looks and works. First part of the identifier is a package name. Usually, it's a project or library you pack. There is another part is package version. It can be any string, but it's recommended that it's typical string with dots, of numbers with dots, because then you can use like ranges of versions. But you can type things like RC1 or something like this if you need. User is the next part here. It means who is the owner of the package. You may use, for example, official Conan packages, then this user will be Conan, but you can build your own, and then it will be like your company name or your private name. You may have your own alternative versions if needed. And channel means the different streams of the same package. For example, it may be different maturity level of the package, not the library itself. For example, you may just created this package like 2 or 3 days ago and you don't know if it's stable. You can say it's testing phase of this package. You may say, for example, that it's built with some specific options for some specific project. This is a specific branch of this build, yes, using this channel. This is basically how the package look on the Artifactory. Basically, it has export directory where you can find Conan file Python or TXT depending on the package. Or probably there's Python for those installed on the Artifactory. And you have different packages for different configurations. When you download it or install to your disk, it looks similarly, but you can find that only one version of gtest was installed because I needed only one. It's not that I'm downloading everything that's on the server, yes? Only things that are needed are being downloaded and installed on your file system. They are stored globally in one Conan directory, so all the projects will reuse the versions if they will have to use the same version. So you will not end up with 10 versions of the same boost version in different subdirectories in different repos. You have one centralized place to store the sources and binaries for the same version, of course. Because if you would like to have different versions, then you will have different hashes here for each version or for each configuration if needed. Or here will be versions, sorry, and here will be configurations. To work with Conan, you can do Conan search to find local cache and list all the libraries you have right now in the local cache. By saying local cache, I mean that you can work offline with Conan. As long as it's already downloaded on your disk, you can rebuild stuff, you can install stuff, and it works. You don't have to access the internet. You can inspect the details of this. I will show you on the next screens how it looks. And yeah, you can inspect also dependencies of current project. I will also show you how it looks. And you can also generate graphs with CMake of dependencies or of configurations you support. This is how Conan info looks. Basically, it provides you information for OpenSSL. That most important here is that this OpenSSL requires zlib, and then automatically the zlib is printed and downloaded and installed on your system because it's a next level dependency on your project that you even don't care about. And this is how Conan search looks for a specific project. It provides you information that this hash that we've seen earlier is built for specific options. These are basically like preprocessor flags, let's say. Or this is the CMake shared option for libraries. And settings, meaning what compiler and what configuration you want to use. If you change anything here, you have a different hash, and it will be a different package on your disk. So everything makes another copy, and you can store them in parallel. And Conan really nicely handles that for you. To install specific package by hand, you can just say Conan install and provide the identifier, saying that you want to generate, for example, for CMake files, and everything will be downloaded, compiled if it's not compiled for your specific configuration, and files for CMake will be generated. But it's not user-friendly, this, so basically you can provide two different files, either Conan file TXT or Python version of this file, with all the dependency and configuration you require for your project. And you just basically provide the path to this file from build directory in CMake, and it will install all the dependencies for you. You can also provide the profile you use. So basically you may have profiles for different compilers, for debug, for release, or specific build types on your disk. Then you don't have to provide any flags on the command line by yourself. And if you provide build missing or build specific project name like gtest, if it will build this project from sources, if it's not built, otherwise it will just exit the installation process saying that it cannot find pre-built binaries for this project. Okay, this is how Conan file looks. It takes the version of it. You have three base groups here. You have requires, saying what are the requirements of your project, specific options that we'll refer on the next slides, and generators will scope on CMake only here because we care about CMake, as I said at the very first slide. In Conan file Python, it's really nearly the same. It's maybe a bit complicated, but we provide the same information in requires clause and in generators here. When you want to provide some options, like saying you want to build gtest in a shared version, you just provide here the option here or here, and then those libraries will be built that way or downloaded that way if available on the server. Or you can also provide those options from the command line with specific syntax. You can also build all the dependencies as shared with star. You will find out when using shared versions that you will sometimes will have problems with linking and execution, saying that you cannot find DLLs needed to execute this library. So there is specific imports clause and imports function here saying that you want to copy all the DLLs to your current binary directory in order for the dependencies to be found. Conan file Python in Python version provides you more power than the text file. For example, you can add here CMake as a module, provide configurations you would like to be able to build with CMake, and provide simple procedure how to build. So this creates CMake's object and configure step, build step, install step, and then you can just build all the project with all the dependencies with these two command lines. You don't have to use any CMake command lines, then just use Conan install stuff and Conan build, and everything is done for you. Also, for example, you can say that you want to specify some options like testing, true, false, and the default option for your package is testing equals false. And then, for example, you may provide the method requirements here, saying that if you are testing stuff, you may want to try this dependency, but for stable builds, just use the previous one that was already checked. So this basically makes some of the requirements dependent on the configuration that you can provide easily, as we've seen during build. And there are many more features here for Conan file Python version, but we don't have time to cover that. Conan profile files looks like this. They have settings, options, environment variables, and maybe some build requirement stuff. They are stored on the in the default profile or anywhere in the project. So you can either have it on your global platform directory or in a project source files. And basically, this is how it looks for my Visual Studio 2017. You have information that's Windows, 64 bits, version 15, release, 64 bits here again this is for cross-compiling, basically. And maybe you can maybe provide, for example, environment variables. Environment variables are mostly useful for example, for Clang, to specify which binary of Clang you would like to use. You can easily overwrite those things, like you can provide it. This is my profile for Visual Studio, but as you can see, it's for release. But you can say build type debug, and you have debug. Or you can create another profile file for debug dedicated for this specific purpose. You can also include some profiles from another profile, so you can make them like dependent on each other. As you can see, they can be put on the disk and then in the project, and then you can refer to them in that way. Okay, so how to use it with CMake? How we are on time? Basically, how I use it, I try to use it in a transparent way right now, as Conan is not an established standard yet on in our environment. Then I assume that the Conan specific part is only used in CMake when this specific file is generated by the Conan. It's found on the disk. If it's not found, I just assume that someone configured stuff in the environment that find package will just work. So for example, gtest root was provided to the environment settings, and it will just work for me. Conan in this file actually provides you the path to gtest root, and this is the power of this file. So you don't have to provide it. It will just provide you the link to or path to specific version of the gtest you want to use, and with that specific configuration. There are some specific options that you could use here. You can either use things that are referred in the documentation. So Conan builds basic setup targets. It will create targets with definitions of all the packages in Conan package namespace, and then you have things like gtest, boost, and so on. But this makes things a bit repetitive, which I will mention on the next slides. So basically, you can use also Conan set find paths only here that will just make the find package to work and don't create any targets for you. Or just directly set CMake module path from the Conan variable that is created in this file. Running both find package gtest and Conan basic setup targets duplicates targets, because as I said already, the Conan will create those those for you, and of course find package will create those. And you end up with 2 targets for gtest, which is a bit a problem right now, as I see with this solution. And there is always a question which one to use. And this basically depends. In general, find package are more mature because they are on the market like for many years right now, but they also have some issues sometimes. Find package basically is really hard to address transitivity, but there is work in progress stuff. I may provide you the link for this. I saw Louis was active there in this thread, but maybe we'll discuss this later on if needed. And it does not support multi-configuration in find package. So if you're using find package, you cannot easily switch in Visual Studio from release to debug to work with. You know that either Visual Studio working in CMake mode will create you 2 directories separate, or you generate also specific solution file for specific configuration. You cannot easily switch from debug to release. Issues with find package are sometimes exist. For example, you cannot build the latest gtest with I don't know if this is the latest or the latest release of the gtest that, by the way, was released like nearly 2 years ago. I don't know if this project is maintained or not anymore, but there are no releases, at least public ones.
There's a new release coming very soon.
Great. So I hope it will build fine on Visual Studio then. But anyway, find package has those problems. And for example, then Conan recipe fixes it in such a way that in package info of Conan file Python, if this Visual Studio and version bigger than 17 or equals to 17, specific flags are appended to the compilation. So in such cases, you may want to use Conan targets, for example, rather than the find package ones. To use Conan package, if there is Conan available, you can use this if statement here. Or with latest CMake 3.11, you can use such an approach of interface libraries for imported targets. It also works fine right now with the latest CMake. I had to skip this subject, sorry. So I will not talk about package creation. I can talk like in half an hour what are the BKMs or creating a package under CMake, under Conan, sorry. I wanted to show you this having 90 minutes, but we had only 45. So for now, please refer to the Conan documentation. It is really great, and you can find a lot of information there. And hopefully see you in CPPCon, where I will have maybe more time to describe it and maybe do some hands-on stuff there, also to show you how it works on the platform. As a summary, many projects still do not use CMake at all. It's a problem right now, as CMake is established standard, in my opinion. Many projects do not use CMake in a modern way, and even if they do not provide means to install stuff and then to reuse them. So please think about this, and if possible, update your CMake files in order to be compliant, to be social, and to work with that. Regarding Conan, it seems that it's a production quality package manager already. It has version 1.0 release last winter. It's free for use, quite easy to use. Documentation is really good. Give it a try. Yes, Titus.
For your concerns about CMake, is anyone like providing a linter for project health and like social project? Like, you are doing your CMake correct. Good job. We need badges or something. Because, like, there's a lot of people that are saying like, we're not doing this great, but no one is actually going out and saying this is exactly how you do it and how you check it without having to be an expert.
Yeah, so basically the question is there any linter for CMake, and the comment that we should have hero badges for those that are doing this great. I don't know about any linter for CMake, but I would really recommend you using this workflow as I shown you. So please, if you are doing everyday builds or during development, use this top-level CMake. It's convenient, it's easy to use, but please consider making your CMake standalone for the library and standalone for testing, and use it in your CI builds, for example, to verify if your package installs correctly and is being imported directly later on by the dependers. So you are sure that it's easy to use, you are social, and it's really good quality package then. This is my recommendation. If someone would like to create a linter for it, it would be great. Yes, question?
So the Conan public repo of packages, it does have a lot of common ones, but like when you get into like the more uncommon libraries that you want to depend on, is there a way to like fall back to the native package manager?
And the question is that, or the comment maybe is that right now in Conan we don't have many packages being packed by the Conan team. Yes, this is true, but there are other also repositories from bean crafters, and there is also Conan community. You can find most of the packages there. If there are some missing, you can either create your own package for Conan, or you can still use just CMake based or any solution based that's the legacy stuff. But I think it's much better if you find that can be used by someone else just to contribute this package to Conan community, and then it will be put to Conan Center. It's pretty easy to create those packages. I hope to provide you DBKMs maybe in CPPCon. We'll see. Yes, question?
Yeah, so throughout the slideshow and on this slide, the word install appears many times, or installation.
Mm-hmm.
So for hermetic build, especially like with in a mono repo or just in general, if you want highly reproducible builds, like having a step where something is installed outside the tree and it depends on whatever version you happen to fling up there is kind of at odds with that. Is there a way to use Conan such that like all the build artifacts are still guaranteed to be completely defined by some root of the project tree rather than depending on steps that a developer might have taken during the build process to install something or
So just to rephrase it and verify if I got you, you would like to make Conan install stuff to your local directory in a project rather than to some global stuff, yes?
Well, yeah, the fundamental thing I like is like you check out my project from GitHub, you build it, and there's a way to guarantee that you are getting bit for bit the exact same thing that I got, right?
Well, you use the same options, right? I think if you use exactly the same options when you're doing Conan install, then that's what you get, I think.
Yeah, so the comment from Louis here is that if you're using the same options for building the project, you should end up with the same binary. It might be true in many cases, but sometimes the recipes are being developed, and they are not stable sometimes, or they are in testing phase. So maybe this will be a bit different build. But if you are using a stable already package of Conan, then it shouldn't change. It should be exactly the same configuration for the same compiler, because as you've seen, the configuration provides you all the information about the compiler version, compiler kind of the compiler version, configuration of this compiler. So I assume it will be exactly the same build for you.
Install dependencies don't include, as part of their name, every option that went into exactly how they were built, right?
Mm-hmm.
So if I tweak a flag and rebuild and reinstall some dependency, it's in the same location. It looks the same to the build system as if I hadn't done so.
I'm sorry, but it seems we are out of time. We can discuss this afterwards because we have like a few minutes to switch to another presentation. So with that, thank you very much. If you have any questions, just contact me during the break or later on.